Next, in the synthesis, the THF ring was introduced. So here we have no THF ring. At the end, we have one. First, TBS protection, hydroformulation of this double bond followed by a Wittig reaction would give this product. By the way, today there's a shorter way to make this. Who has an idea? This is not the best Lösung, the best solution. That can be made faster. Who has an idea to make a one-step conversion of this olefin into this olefin? What could you make? Metathesis, olefin metathesis today would be better. So with some standard procedures, we convert this compound into the iodide, make an iodine lithium exchange, and add to the aldehyde. Again, we have a 1,2 induction, 5:1 selectivity, and then the THF ring is closed by generating a tosylate, a leaving group here, hydrogenolysis of the benzyl ether, and then an intramolecular Williamson reaction gives us the THF ring. The end game of the gymanysine synthesis starts with the Mitsunobu reaction to introduce a thioether that is oxidized to the sulfone. Then a Julia-Koczynski olefination of the sulfone with that aldehyde completed the carbon skeleton, and finally Wilkinson hydrogenation of this double bond. That's the normal double bond, that's the electron deficient double bond, only this one reacts, and final deprotection leads to gymanysine. You don't have to learn all the details, but please keep in mind the intramolecular epoxide opening and the intramolecular elaboration are very efficient solutions for the synthesis of the THP part of these natural products and for the total synthesis of these two compounds. So that was my example from the natural product thing, and that brings me to this question. So now I would like to discuss with you the answer to this question. First we make a vote. So please vote. Who thinks cis is faster and who thinks trans is faster? Who's for cis? Who's for trans? You say trans. Why? It's not only important to have an opinion, but also to have a reason for this. Why would you say that trans reacts faster? What would you? Okay. Well, he points out it is important to know the structure of the molecule. This is a flatland representation, and that's not a true. So how does the molecule looks like in 3 dimensions? That's the first point we have to know. And he says it is a chair. Do I have my, yeah, here. So first you have to know the conformation of the molecule. And then you have to know the mechanism of the reaction. So let's talk about the conformation first. It is a chair conformation. The tertiary-butyl group is a conformational anchor. It will always go into an equatorial position. For the cis case, this is the preferred conformation of the molecule. For the trans case, this is the preferred case of the molecule. So in the cis case, we have an axial alcohol, and in the trans case, we have an equatorial alcohol. So the question really is, which alcohol is faster oxidized, the axial or the equatorial alcohol? That was the first step. We translated the question into the real question. You understand? So let's ask the question again. Which alcohol is faster oxidized, the axial or the equatorial alcohol? In order to answer this question, you have to know the mechanism. What do you know about the mechanism of chromic acid oxidation? I assume you learned that during your bachelor, or? Who can tell me anything about the mechanism of a chromic acid oxidation? What have you learned? You, yeah? What we are discussing here is very general, and I think it's very important. If you want to contribute to chemistry, not only organic chemistry, but chemistry in general, you have to know the structure of the problem and you have to know the mechanism. So the mechanism of the chromic acid oxidation is a two-step mechanism. In the first step, how about space? So that's the other way of writing the question. And the question is, which one is faster? The first step of the mechanism is the formation of a chromic acid ester. I write it in general using cyclohexanol. an alcohol and an acid lead to an ester. So this chromic ester is formed in the first step. That's the first step. In the second step, oxidation means the metal wants electrons. This is the important arrow. The metal, the chromium, loves to have electrons, these ones. That results in the breakage of the carbon-hydrogen bond, and that leads to the product. That's the mechanism of the chromic acid oxidation of an alcohol. Again, my question, which one is oxidized faster, the axial or the equatorial? Now you have the information. Now make a prediction. What would you do? Make a prediction. Now I gave you the mechanism. What would you guess? Axial or equatorial? Why? Which position is better accessible, axial or equatorial? The equatorial position is better accessible. So the formation of the chromic ester is easier here than there. But what is the rate limiting step of this two-step mechanism? The formation of the chromic ester or the oxidation step? So it's very important, if you talk about a multi-step mechanism, to know the rate limiting step. Otherwise, you will never get a good prediction, because he will say, well, the equatorial chromic ester is formed better, and he may say, but there are arguments for the other step which point in a different direction. If I have a multi-step mechanism, I have to know the rate limiting step in order to make a good prediction. So what is the rate limiting step of the chromic ester oxidation? Have you learned that somehow? It's the second one.